All right, hey everybody. It is 20 minutes after 7. I apologize for the late start. We're having some technical difficulties yet again with our broadcasting setup. Welcome to the August meeting of the Madison Astronomical Society. I'm the president, Lawrence Moore, and it's great to see everyone here this evening. I'm going to try to jump through some announcements as quickly as possible. First of all, tomorrow night we are having an open club star party for Madison Astronomical Society members at Yana Research Station at 7:30 o'clock. And it should be kind of nice since the Perseid meteor shower is should be at a maximum. And last time I looked, the weather forecast was looking pretty promising, so we hope to see people out at Yana Research Station tomorrow night, and we will make a weather call by 4 p.m. in case we decide that the skies are just too cloudy to expect everyone to show up. So we hope to see you there. Also coming up, we're having a public outreach star party at Donald Park, and we haven't been able to pull off a star party there in quite a while. I think last year we had bad weather, and before that we had issues with the COVID outbreak, the COVID pandemic. So I just wanted to, in case anybody was interested in volunteering a telescope or some binoculars or a laser pointer and some knowledge of the night sky, we are going to it's going to be on Saturday, August 19th, and it starts at 8 o'clock p.m. and we will be setting up near the Pops Knoll picnic area at 6:30 and afterwards. And if anyone is interested, just a reminder that we won't have electrical outlets available there. Next month's meeting is on Friday, September 8th at 7 o'clock. And it looks like John Rummel will be presenting a lecture called Why Solar Eclipses Matter and Why Totality Matters More Than Anything. John, would you like to give a little bit of a teaser?
I think that title is great. Totality Matters. So it's basically going to be an introduction to two eclipses, because there's an annular in October, and then we're going to have another eclipse talk in March, basically talking a little bit more about photography and what to do if you want to take pictures of the April eclipse. So that's next month.
Thank you, John. That's great. Also, unfortunately, I do have some.
I don't think I can keep.
Oh, okay. That's all right. We also have sad news. Longtime club member Win Wacker has died. We are considering right now having some sort of memorial observing session or some other event. Stay tuned to hear more about that. We just heard the news this morning from Win's sister. So, Lawrence, you want me to take the rest of the announcements?
Yeah, I'm okay.
Okay.
Yeah, thanks for sharing that. And luckily, these sort of situations are always things that we hate to encounter, but it kind of, fortunately, he did. We do have a plaque with his name on it for one of the pads, and this is another reminder. You just never know, and it's just one of the things I like about being a member of this club is it's great to fill people's lives full of random happy memories. So it'll be great to remember. He's been a member for a long, long time, since the 1960s, and it was always great to have him around to hear about his tidbits of knowledge and wisdom. So yeah, he's going to be missed. We have a special guest. This is about the time where I normally ask if anyone's visiting Madison Astronomical for the first time ever. Oh yes, I'd like, if you don't mind introducing yourselves to the club.
My name's Tony Reeves. I was a statistician with Wisconsin Department of Health Services until about a year or so ago, and now I'm retired. And I've been intending to do this for a while. I have one of those weird telescopes that was designed to commemorate the whatever anniversary of Galileo's first identifying the moons of Jupiter. And I guess I can contribute that if we're going to be going to any kind of star stuff.
It's nice to meet you. Thanks for being here. And yes, what's your name?
Hi, I'm Jan. I'm recently retired from the Wisconsin Department of Justice, and I'm brand new, so I don't know anything about this, but I'm really interested.
Great. It's great to have you. This is the perfect place to show up if you're just new to astronomy and want to learn more about the hobby and how to observe. This is the perfect. I encourage anyone that's out there listening to this and watching us. This is the best place to show up and learn about the hobby. What's your name? Jan. Great to meet you, Jan.
Yeah, thank you.
And we also have another special guest here. Yeah, we have Al Schneidler from the Astronomical League.
Yeah, Al Scheidler is my name. I'm the chairman of the North Central Region of the Astronomical League, and I've seen so much good things on internet, Facebook and so forth, what you folks are doing, and so I thought I'd come up here and introduce myself. I am with the Astronomical League, but my club that I'm a member of and a past president of is the Popular Astronomy Club in Moline, Illinois, so it's not too far from here. And anyway, I thought I'd come up and just introduce myself, see what you guys are doing, see if you have any questions for me, and I'm here. So, any questions? I guess I'll turn it back.
I do happen to know at least one of our members is working on an observer qualification. So yeah, I'm sure people would be more than happy to shake hands and get to meet you. All right, we got a little bit of time to spare. I just interested in case anyone has some recent astronomy recent stories of observing themselves or any interesting astronomy news they'd like to share with the club. Now might be the time to speak up if you have anything to share. If not, in spite of starting late, we still got a few minutes to spare.
I will just mention for the new members, I said there, for the new people here, tomorrow night's Star Party is a really good place to get a feel for things.
And that reminds me something very important that I left out of my notes. I do have an important announcement that a lot of us who have been attending meetings over the last few months are aware that we are going to begin an important renovation project at Iana Research Station. And I just wanted to let everyone know that the construction there is going to be beginning on Monday, August 21st. Although, of course, with any kind of these kinds of projects, any kind of quirk or delay with the contractor might cause that date to move around a little bit. So things might be a bit more chaotic there than what we're used to. So if any of us were planning on maybe using Iana Research Station, we might not be able to use any of the ground that we're used to using. There, Jürgen?
I just wanted to say that
Oh, yeah, let me.
suspending myself. The anticipation is 1 week for them to do it, but then the ground's going to be disturbed afterwards, so don't try to use it the week of the 21st. I think Lawrence will probably send out a note saying that they actually have started. And I don't think there's going to be any weather delay based on what the weather has been saying, so.
Yeah, thanks, Jürgen. And we're trying to figure out if anyone out there knows any connections as far as delivering massive amounts of water to Iana Research Station. We do not have any kind of water service there. I had just, after my home construction last month with, I think we were impacting about 2,400, 2,500 square feet of our ground at Iana Research Station. At my place, I was around the 1,700 square foot. And I think if I remember right, watering the new grass every day, I was using about 130, 140, 150 gallons per watering. So yeah, we're gonna have to figure out some system, at least of having the ground recover well, or having a way of delivering that amount of water to get the grass to grow quickly. So if anyone, yes.
John Young has an irrigation well up at his place.
Yeah, we're aware of that. So, but yeah.
I remember long hoses being used to get water down.
Oh, really? Yeah. That.
But when you think of the other options.
Yeah, that's good. That's good to be reminded about. I wasn't aware of the hoses. And,
Did we reach out to Carson and he didn't think it was feasible?
it's quite possible, because I think I remember him mentioning that there was a limited, based on his well, that there was a limited supply of water in his well, but I'd have to.
He said it was kind of like a large dribble.
Yeah, a large dribble. Okay, his water supply from the well there on the Anna property is a bit like a large dribble. So I knew there was some reason why we didn't follow up with him about that. So I appreciate the tip. So I see that it's 7:30. John, would you like to introduce tonight's guest speaker? Thank you, John.
Thanks, Lawrence. Just a quick word about Win Whacker. When I scheduled tonight's speaker, who I will introduce in a moment, Pat Fry, Pat's going to talk about Jupiter tonight. And some of you may know that Win, back in the day, was extremely involved with the Association of Lunar and Planetary Observers, specifically with the Jupiter chapter. Win was a Jupiter freak. And when I scheduled this talk, I thought of Win, because I knew how much Win would enjoy hearing a talk about Jupiter. And so I am devastated to hear that of Win's passing.
I just want to jump in. I just had an idea about Win. His family, I've been talking to his sister, and MAS was a very big part of his social life. He didn't have a lot of strong friends and connections outside of it, and his sister has been kind of surprised and pleased to hear some of the things we've had to share with her today about his involvement with the club. If anyone out there has any stories, anecdotes about Win, please send them on to me to the club email address, or to any of the board members whose email you might have, and we will pass them along, because I think Win's sisters would really enjoy hearing them.
I'm going to be getting her name and number from you, because I want to call her for sure.
He was my best friend since 1964. This is the first time I found out he's going.
Yeah.
Came to the meeting.
Sorry to hear that, Eric. Eric's and Win's names and identities are very closely entwined, going back to the junior blank on the name, the Junior Society back in the 1960s. Yeah, yeah. So, sorry to preface, Pat, with that bit of bad news, but I do want to introduce Pat Fry, one of the very few people at the UW-Madison who actually does research inside the solar system. Pat is going to, first of all, Pat got his degree at UW-Madison in engineering, started working here soon after, and has spent his whole career at UW-Madison in space science and engineering, right? Very involved with the James Webb Telescope, which some of you may have heard of. And so I did definitely invite Pat to share stories, not only of his research in the science, but just also of what it's like to work on a project like the James Webb. So please welcome Pat Fry.
Thanks very much, John. Can everybody hear me okay? All right. Real quickly, my degree was in computer science, not engineering. No, I started out as an engineer. That's probably where you got it from. But, all right. And it's great to be with you guys here tonight. I'm sorry to hear about your losing a member. It's very unfortunate. Tonight, I'll be talking a bit about the James Webb Space Telescope and its ability to observe solar system targets, some of its capabilities, and some of its scientific instruments. and also some specific observations of the Jovian system. Webb has several key areas of scientific interest. Searching the first galaxies that formed in the early universe, studying galaxies near and far to inform the evolution of galaxies, observing the life cycle of stars from the first stellar nurseries to the formation of planetary systems and also the death of stars, measuring physical and chemical properties of planetary systems, including our own system, and investigating the potential for life on planets that orbit other stars. So you'll notice that including our own solar system is a ways down the list, but still it's very important. And many of James Webb's capabilities were actually implemented just so that it could observe things within the solar system. If you think about it, having a space telescope that wouldn't be able to point inside the solar system or track targets would be a great loss. So I'm part of a team that was headed by Imke de Potter, who's at UC Berkeley, and Thierry Fouché at the Observatory of Paris. We and a bunch of people, at least 60 people altogether when the program first started, proposed Jupiter observations to the Director's Discretionary Early Release Science Program at STSCI, the Space Telescope Science Institute, back in 2017. The program's goals were to demonstrate Webb's capabilities with some of the very first science observations performed by the telescope. There were many parts to the rationale for observing the Jupiter system, and including Jupiter is a large, bright, and rotating object, so we need precise pointing, geometric correction of images, and accurate tracking, e.g. tracking for great red spots, we can observe it and other features on the planet. Jupiter is orbited by faint rings and tiny moonlets, so large dynamic range requirements are in existence, and we must deal with a lot of scattered light from the planet itself. The spectra of Jupiter exhibit faint emission and absorption lines on a bright continuum background, which make them hard to see. And the system displays dynamics and timescales from seconds to weeks and longer. For example, aurora, volcanoes, storms, and impacts. So, as part of our program, we wish to characterize Jupiter's cloud layers, winds, composition, auroral activity, and temperature structure, and also produce maps of the atmosphere and surface and volcanically active Io and icy satellite Ganymede to constrain their thermal and atmospheric structure and search for plumes. We also aim to characterize the ring structure and its sources, sinks, and evolution. And here we show an image of part of the Jupiter system. It doesn't show any of the big moons, but on it you can see the planet itself and the rings, some of the tiny moons around it. And you can also see some of the artifacts that we see in the images, such as the scattered light. It slipped several times after there were studies, more studies, and cost analyses and things like that, to eventually Christmas of 2021 when it was launched. After 6 months of commissioning and calibration observations, it began its science observations in mid-2022. Our program includes observations that challenge many of the capabilities of JWST. We were also some of the very first science observations of it, and one thing that was sort of a coincidence was that the observing window for Jupiter opened up like the day after they began science observations. So we were really some of the very first observations done. So let's take a look at how we accomplished some of these goals. And it requires a pretty amazing observatory and a set of scientific instruments to do all of this. First of all, where can JWST observe? As you may know, it is placed orbiting the Sun-Earth L2 Lagrange point, which is opposite the Sun, away from the Earth, which is about 1.5 million kilometers from the Earth, which is about 4 times the distance of the Moon. While it's out there, It has this sun shield, which has to keep the telescope and all of its instruments cool, and because of that, it can only point the telescope is on the far side of the sun shield, and it can rock like 50 degrees towards and away from the sun, from 85 degrees to 135 degrees away from the sun. It can also rotate about the axis to the sun, and near the ecliptic, which is where most of the solar system objects are, it can view looking forward into orbit and looking back. So because of that, you actually get 2 roughly 50-day observing windows per year that you can look at a particular object. And the roll angle options for objects near the ecliptic means that you don't have a lot of leeway as to how you orient the science instruments while looking at a target, which has certain ramifications when you're trying to align, say, spectroscope slits up with certain features on planets and things like that. So what special capabilities does JWST have for solar system observations? It has an ability to track moving targets, which, as I mentioned, is very important. It can track planets, satellites, asteroids, outer solar system bodies, trans-Neptunian objects, comets, etc. It has to be able to slew relatively fast to track some of these objects like asteroids and comets. It has different levels of targets that it can look at. It's sort of a hierarchy. There are level 1 targets, which are bodies directly orbiting the sun, such as planets, comets, or asteroids. Beneath that, there are level 2 targets, which are relative to level 1 targets, such as moons or positions relative to the level 1 targets, for instance, latitude and longitude on a major planet. And beneath that, there are also level 3 targets, which are positions relative to a level 2 target. So you can point some ways away from a moon, or you can look at a moon's latitude and longitude and things like that, and the telescope will track those things for you. Continued, what other capabilities does it have? It has to be able to observe bright targets. Compared to other targets that it was designed to observe, many solar system objects are very bright. And because of this, we have to use narrow wavelength bandpass filters or high dispersion spectral elements. And we can also read out subarrays of very large detectors for shorter exposure times. I'll talk about that a little bit later. And despite these characteristics, there are still some bodies that are just too bright to observe at some wavelengths. So let's look at the instrument focal plane. Here are the footprints of various instruments as projected on the sky. The instruments include NIRCam, the near-infrared camera, NIRSpec, the near-infrared spectrograph, MIRI, the mid-infrared instrument, and NIRS, the near-infrared imager and slitless spectrograph. Let's start with the main imaging instrument, NIRCam. All the detectors are 2K by 2K pixel Mercad telluride arrays with wavelength range from around 600 nanometers, which is in the visible red, to around 5 microns in the infrared. So James Webb is not able to look at all of the visible wavelengths like Hubble can, and so there isn't an overlap between them fully in that way. So one thing that this actually informs is that when Hubble is no longer able to make observations, we lose a great capability because Webb can only look in the further infrared and just in the red and the visible. So one thing that they're doing at Space Telescope Science Institute is actually prioritizing the very most important observations that Hubble has to do before it's gone and we're left with just Webb as the main observatories in orbit. All right, back to NIRCam. The short and long wavelength channels of the camera view the same areas of the sky simultaneously. So you can see there's a module A and module B, and within those modules there are 4 short wavelength detectors in a square with gaps in between them, and also Optically, they're looking at the long wavelength channel, which is looking at the same region of the sky, which is, it's actually the same size array, but optically it's configured so that the pixel size is twice that of the shorter wavelength array, so it covers the same period of portion of sky roughly as the shorter wavelength 4 detectors. Different spectral regions of the light that we detect are affected by absorption or emission processes of various gases or condensed particles. So you can see in this spectrum that when we look at the shorter wavelengths that Webb can look at, we see, for instance, methane absorption and some ammonia absorption. But then we get to the longer wavelengths, out past 5 microns, where we're looking at some excited molecules, but also looking at just pure thermal absorption of ethane and methane and things like that. And the longer wavelength is actually very useful for looking at very cold objects in the solar system. So the near-infrared camera has filters that can image certain spectral regions. You can see here that it has essentially 4 sets of filters. There's a very wide band set of filters, then wide, medium, and narrow bandpass filters. Note that there are relatively few narrow bandpass filters in the set. And you can also see the wavelength break between the short wavelength module and the long wavelength module of the camera here, which is at about 2.5 microns is the break point. Okay, so this plot shows the brightness of the giant planets compared to the saturation levels for the various NIRCam filters. The Jupiter spectrum is light orange on this plot, and it saturates in many of the wide and medium bandpass filters, so it's just too bright for us to look at in the normal configuration where we read out the entire detector. Each readout in that configuration takes about 10 seconds, and that's just too long for as bright as Jupiter is. The narrow wavelength bandpass allows viewing bright spectral regions, but there are only so many of those filters. And where the objects are still too bright, we can actually use subarrays to look at smaller portions of the sky, and because of that, you're reading out fewer pixels and can read at a faster rate, which reduces field of view. Here we can see the full arrays in the 2 channels, and as you get smaller, there's the sub 640, and the sub 160 is the smallest subarray in the middle of all of that. And you can see that the long wavelength channel, you still get the full square, but it just gets smaller because the arrays read out the same number of pixels for the short wavelength channels and the long wavelength. And you can also see that when you get down to the very smallest subarray, like the sub 160, the red square, which is the long wavelength channel, is actually smaller than the extent of the shorter wavelength, but you have these big gaps in the shorter wavelength, so you're actually looking at 4 little rectangles with big gaps in between them for the short wavelength. And because of that, you have to do mosaicing or dithering patterns to cover larger areas and to fill in gaps between the arrays. Okay, as I said, the same number of pixels are read out for the short and long wavelength channels. Also, the same readout pattern is used for both channels, complicating exposure planning. So when you plan your short and long wavelength observations, those exposures happen at the same time, and they have to have the same exposure time. There are certain things that are done that allow you to look at slightly brighter and dimmer objects in the visible or the short wavelength and the long wavelength, but it's sort of a juggling game to get both of your exposures to happen at the same time with different filters. And note that the relative size of the interdetector gaps for the sub 640 array left and the sub 160 subarray right vary quite a bit. So here, when you're looking at the whole planet in the sub 640, the gaps here aren't very big compared to what you're looking at altogether. But if you can see down here, when you're looking at these little, like the purple squares, which are all one exposure, you know, with 4 different arrays, you have a big gap in between them. So you can see that you have to do a lot of moving around to cover larger areas. All right, so, and here are some examples of Jupiter as seen through the different filters. As an example, we can see high altitude hazes in the F212N image in the upper left at the poles and near the equator. So you can see that you don't see any detail at all at the poles there because there's hazes over that, meaning making it so you can't see further down. And in the longer wavelength channels along the bottom there, you can see the north and south polar aurora. All right, so what do we learn from these images? So the first thing to see is that the different filters probe to different depths in the atmosphere, and that's because there are different gases that absorb at various locations. And if there's a certain gas that absorbs a lot, but it doesn't actually occur in the atmosphere until further down, you can look further down in the atmosphere. And also, we can use the different filters and take multiple images with time in between, and we can measure the winds at the different levels of the atmosphere. So the plot on the right has an example of the winds that are measured in 3 different JWST filters, the F164, the F212N, and the F335. All right, so now let's go to a different instrument. Let's jump back to the full focal plane layout here and look at the near-infrared spectrograph, which is up in the upper left-hand corner. One thing to note is that all of its detectors are rotated about 138 degrees with respect to all of the other arrays in the focal plane. And this has some impact when you're trying to look at various features on the planet and line some of the spectrographs up with features or with the planet's pole or something like that. And the problem is that you can't take this whole focal plane and just roll it, you know, one direction or the other. The telescope can actually roll like only 5 degrees one way or the other until the sunshade starts letting light onto the telescope and warming things up. So you're sort of stuck with this orientation of these arrays relative to each other, which is a little complicating at times. But I'll show a little bit of that later. And let's look a little closer at the NIRSpec focal plane here and some of its observing modes. One interesting thing I can do is multi-object spectroscopy. And this utilizes a microshutter array, or MSA. And these 4 separate MSAs together make up about 250,000 shutters that can be individually commanded open or closed. So because of that, you can do things like look at a field of stars and just look at a certain number of stars at one time. And when you look at only a few of them, the spectra that you're dispersing onto the detector, they don't overlap if you open your array, the microshutter array correctly. And some shutters are stuck open and some are stuck closed, unfortunately. But that is a well-known thing, and there are maps of those open and closed shutters, and you sort of work your way around those when you do your observations. There's also an IFU spectroscopy mode, and IFU stands for Integral Field Unit, and I will talk about that in just a moment. And there's also some fixed slits for fixed slit spectroscopy, and you can see those, you know, right in the middle of the field, right down here in between these MSA arrays. And so those are all dispersed well, first, all of these are dispersed in the left-right direction in wavelength. So when you open up a shutter or something and take a spectrum, the spectrum that comes out, comes out horizontally in this particular orientation here. So these little slits in the middle of the field here do not overlap with the microshutter arrays at all. So you can take spectra in the microshutter arrays, and you can also use the fixed slits in the middle, which are of different sizes and different widths and things like that. And there's also this IFU unit, integral field unit down here in the corner, which is a tiny 3x3 arcsecond instrument, and I will talk about that now. So traditional long slit spectroscopy can only view a narrow bit of the sky at a time. You just line up a slit and you let some light in, then it goes through a grism or onto a grating or through a prism, and you get a spectrum out of it. With an integral field unit spectrograph, a portion of the sky is sliced into narrow sections, and those sections are offset so they can be dispersed into non-overlapping spectra. These spectra are then recombined to produce images at individual wavelengths. These image cubes can also be viewed as individual spectra for each spaxel of an image. So a spaxel is essentially like a pixel in an array, but it's something that you get a full spectrum out of each particular spatial area. And also shown in the lower left here is the image slicer that performs some of this optical magic. So if you think of it, there's a field that's imaged onto that rectangular area, and each of those little portions of the slicer reflects that little slitlet of light on a different angle and puts on it at a different place on the array. So a slightly closer look at the IFU here. It covers a 3x3 arcsecond area, which is fairly small. For comparison, Jupiter is around 50 arcseconds in diameter. So when you're looking at that small of sky, that's something very small compared to Jupiter. And that 3x3 area is split into 30 vertical slitlets, we'll call them. And this image slicer projects these slitlets onto non-overlapping locations on the detector array. And the individual spaxels are 0.1 by 0.1 arcseconds in this 30 by 30 array. And the spaxel vertical size is determined by the detector pixel size that they're projected onto. And you can see here that the projected slit locations for the IFU are at the left in blue. And so that little square of the IFU gets split up into the 30 spectra, and you can see them lined up along the left-hand side and how they are set up on the detectors. And while you're doing this mode, the microshutter arrays are commanded all closed, so there's no light getting through there to spoil the spectra, although that's not completely true because, as I said, there are shutters that are stuck open, and you also just have to work around those as well. And another thing is that even when the microshutters are closed, there's still some leakage through them. They're not exactly perfect. And what I'm showing here, the circle that I'm showing, is the approximate size of Jupiter. And say we're looking at a southern mid-latitude location there on the planet, you can see that another portion of the planet is actually impinging on one of the microshutter arrays. And what you get is, even though there's just a little bit of leakage through these microshutters, you can actually get the spectrum ruined a certain amount because of that. And there are ways around that. You can actually do a background exposure where you then just close the IFU shutter and then expose, and then you know what the background that you have to subtract off is. But the problem with that is it takes twice as much time as a normal observation would. And for this whole program that we're doing, we only had 40 hours of observing time on the telescope. And it became a very valuable resource. And so we looked at the ways that we could actually get away with not taking as many of these background exposures as possible, and trying to find clever ways to take out the artifacts without incurring additional exposure time. Okay, and there are low, medium, and high resolution spectral modes of this IFU. So you can see that there's one mode, which is a prism mode, which covers the entire 1 to 5 or 0.6 to 5 micron range. And there's also some lower resolution, R equals 100, where R is the resolving power, which is the ratio of the wavelength to the actual spectral resolution that you're looking at. So, for instance, if you're looking at 1 micron wavelength and you have a 10 nanometer spectral resolution spectrum, that is like a R of 1000 spectrum. And the medium and high resolution modes require several exposures with different spectral elements to cover the entire range. And the way the software for the telescope is set up, when you're doing a mosaic of a region of the planet or something like that, you have to do the entire thing in one wavelength, and so you're in one wavelength mode, and the telescope points all around to do your mosaic. Then it switches to the other mode and does its mosaic again. And on non-moving targets, that would be fine, but it's a definite complication when you're looking at a rotating body like Jupiter, because you're looking at the same mosaic pattern, but it's looking at a slightly different portion of the planet. It's still pointed at the same location for the mosaic pattern, but everything moves around a little bit because of the rotation. And another thing about the high resolution modes of NIRSpec is because there's a gap between the two detectors, there's actually a wavelength gap in all of these spectra that you're getting. And that's another thing you have to take into account for your observations and just sort of have to live with, because there's really no getting around that if you're still using the same high resolution mode. And you just have to hope that what you're looking for, well, you don't have to hope because you know, but you have to limit yourselves to spectral ranges other than those gaps, because you just can't get those. And let's look at 2 observations conducted by the NIRSpec for this ERS program: the Great Red Spot region and the South Polar region. The small 3x3 arcsecond field of view necessitates mosaics for all but the smallest features on Jupiter. Remember that only 2 roll angles are available for objects near the ecliptic, Jupiter being one of those, and tiles are not aligned with Jupiter's pole. So what that means is that mosaics are specified by a number of tiles, rows, and columns, and then you also have to specify the angle that each of these tiles will make with respect to the other ones based on just the spacing between them. They can't roll an angle. You just specify the distance that it goes when it steps to the next row and things like that, and you can determine how much overlap there is between the tiles. And short and long wavelength ranges are acquired separately, so remapping is required to overlay different wavelengths on planetary lat-long grids. And here's an example of that. This is 3 wavelengths of one of our Great Red Spot observations here, and you can sort of make out where the 6 tiles of this mosaic are. This is actually earlier in the processing, so you can still see some artifacts which allow you to see the edges of the tiles better. And in this particular RGB image, the green and blue channels use one particular spectral element, so those are taken at the same time, but the red portion of this image was taken about an hour later, so the planet had rotated at that time, so all the tiles don't quite match up, even though the center of the pattern is the same in each cases. Another thing to notice here is that there are certain spectral regions that are too bright for this instrument, even in its highest spectral resolution mode. For instance, the Great Red Spot and the South Equatorial Belt region, which is up at the top of this mosaic, are both saturated to some extent around 2 microns and a little bit shorter. And the hot color around the Great Red Spot in red here is actually a region where you can see further down into the atmosphere, and where it's warmer, and that being as bright as it is, we can't actually see longer wavelengths, where it's starting to warm up in this 4 to 5 micron range. So we're essentially losing all the information out here from these regions where it's red. But there's nothing we can do about that. And here are some other results from the GRS observations, looking specifically at the ionosphere above it. The upper image shows a typical view of the GRS at visible cloud level, and the dominant ion in the ionosphere is hydrogen 3+, which emits in the 3 to 4 micron range. So we look at those specific wavelengths, and from that we can tell things like what the temperature is of the gas high up in the atmosphere. And there's a surprising amount of small-scale structure seen in the ionosphere in the lower image here, and it was totally unexpected. And some of the scientists are still trying to figure out what that means, whether it's means that there are, for instance, more particles, or whether it's small-scale temperature differences or density differences, and they're still trying to work that out. All right, and finally on to the mid-infrared instrument. This covers a longer wavelength range in the 5 to 30 micron region, and that's good for exploring cold outer solar system bodies, and it also is good for searching for spectral signatures of organic compounds and other gases in the giant planets. The imaging array, it has imaging arrays and another integral field unit. It has actually 4 of them. I'll get to that in just a moment. And if you see up in the upper right-hand corner, that's the MIRI aperture set there. And this little orange square up in the corner here is the medium resolution spectrograph, which is the IFU module for MIRI. So there's a set of 4 separate IFUs viewing roughly the same patch of sky, and each IFU covers its own wavelength range in 3 different steps. So together they can cover the entire 5 to 30 micron spectral region. The shorter wavelength channel has the smallest footprint on the sky. That's the, I guess it's blue in this case, channel 1, and the longest wavelength channel 4 in red, has actually a much larger field of view, but they do for the most part overlap. And here's a model Jupiter spectrum below that shows where you can see some of the molecules that are sensed in this wavelength region. If you look out to the right there, the 5 to 10 micron region, you can see certain gases like germane and water and ethane and more methane and ammonia and H3+. Well, that's actually in the shorter wavelength. And above that, you can see the different channels of the MIRI medium resolution spectrograph. So you can see there are the 4 main channels, and within each of those, there's 3 sub-channels which have to be looked at separately to cover the entire spectral range. And just to give you an idea of what the optical layout of this instrument looks like, I'm always amazed by this. It's a very complicated instrument, and the light is first sequentially split into 4 channels with 3 dichroic filters. So a dichroic is essentially a mirror that reflects shorter wavelength light and transmits the longer wavelengths. There are 3 of those in a series, and this results in 4 different wavelength channels in the instrument. So if we look at it, let's say we just want to look at one particular channel here. So this is the main input here, and let's say for channel 1, this is the first dichroic. So the shorter wavelengths of this get bounced back to here, over to here, to a couple of different steering mirrors and other optical elements, and finally it comes out here, and that goes to the portion of the instrument which has another image slicer and which is actually separate from this diagram. And if you want to look at the second channel that goes through here, gets to the second dichroic, which splits off, another portion of light, which bounces around and eventually ends up over here to the second IFU, and then onward with channels 3 and 4. So it's a very complicated instrument, but it works for the most part good. They're having a few problems with some of the longer wavelength observations and some of the software processing it and reconstructing the images with it, but I'm sure they'll make progress on it. Just to give you a little background, I was mainly involved with the Infrared Spectrograph. That was the second instrument that we talked about, which did the Great Red Spot and South Polar observations. And so that's the main instrument that I have actually worked with, although for some other proposals that we did, looking at Saturn, for instance, I also worked a lot with the NIRCam imager. And getting back to the MIRI MRS IFU again, here's just an example of the size of those various footprints for the spectral channels on Jupiter. And you can see that when you're down there, you don't get an awful lot of real estate to look at, compared to the whole planet. And so what was done for this observation, when they're specifically looking at the aurora and the long wavelength portions of the aurora, is they built up a mosaic of the South Pole by just sitting and staring and looking at the South Pole and letting the planet rotate underneath it with its 10-hour rotation period. So, and real quickly, I'll go through a couple other results other than I have mentioned at this point. First of all, there were some ring observations, and I'll start with those. And as this diagram shows, there's the main ring bounded on the outside by the satellites Madison and JWST. Interior is the so-called halo, and the yellow and green rings are the gossamer rings bound on the outside by Amalthea and Thebe. These are, of course, the smaller moons of Jupiter. And we identify the following outstanding questions in our ring observations and investigations. Where are the source bodies for the fine dust? And explanations for various observed clumps and asymmetries in the rings are another thing that we look for. We also look for the role of the magnetosphere in how the rings clump and do what they do. And we also look at the composition and physical properties of the moons and the dust. And as shown in these movies from the NIRCam images, we had two sets of observations rotated on the sky by about 10 degrees. So you can see the ring changes a little bit in its angle right there. And the reason we did that was to facilitate modeling and subtracting the background and scattered light from Jupiter, which is so much brighter than the rings themselves. And note the tiny satellite JWST and Thebe and JWST. Oh, someone else wrote this. and note how well we can see the rings, and even there's a little notch in the rings that you can see at some point here. And so far, there is no obvious indication of any smaller, previously unseen moons embedded within or near the rings. The evidence for arcs and other ring asymmetries is marginal at best, and we are somewhat surprised by our inability to detect the outer gossamer rings, which we expected to see because they are only 10 times fainter than the main ring from other observations, for instance, from Voyager or from Galileo. And this isn't an IFU image, but it is an image of Ganymede showing roughly the size of the NIRSpec IFU spaxels on the moon. And in order to understand the processes that shape Ganymede's surface and atmosphere, or exosphere as we also call it, we need to identify and quantify the surface composition and the gases in the exosphere. This image shows the NIRSpec IFU spaxels overlaying a higher resolution image. And the spectra show, for instance, a carbon ice spectrum. We can see solid state features in the spectra, like the Fresnel reflection peak near 3.1 micron, which comes from the reflection off facets of grains in water ice. We see this and the CO2 ice very clearly, as well as the 13CO2 isotope, and a new feature which is not seen before, which is hydrogen peroxide. There are some hemispheric differences and variations with latitude, as shown in the next slide. Here are two images of the CO2 ice band depth on the leading and trailing hemisphere of Ganymede, where the ice is clearly concentrated near the equator. On the right, we show that the center of the CO2 band is shifting toward longer wavelengths at higher latitudes. We do not yet have an interpretation for this shift. It may be due to variations with temperature or to different types of CO2 bearing phases at low versus high latitudes. Here are the image of the Fresnel peak equivalent widths on the leading and trailing hemispheres of Ganymede, which shows a very large difference between the hemispheres and much stronger peaks at higher latitudes. The hemispheric difference may be caused by variations in temperature and or grain size, which may be related to changes in surface roughness at sub-millimeter scales. The latitude variations may reflect a redeposition of water at the poles, resulting in finer grained ice. We also observed EO in eclipse with JWST on 15 November 2022. Two images averaged over 0.01 micron are shown, as well as a reprojection superimposed on a USGS map of Io's surface. There is a very bright emission from Kanakakili, Fluctus, and a fainter from Loci Patera, two of the volcanoes on Io. The Loci Patera is on the limb of the satellite. Spectra are shown here for the integrated flux of Io and the Kanakakili, Fluctus, and Loci Patera volcanoes. So we modeled these spectra with a combination of blackbody curves as indicated. Clearly, as expected, we see lavas at temperatures over a range of values from 300 Kelvin up to 1500 Kelvin. All right, and that is what I have so far, and I'd like to leave this up if I can. Here are places where you can find much more information about the telescope and its observations if you wish. There's the webtelescope.org site where you find some of the higher level information about the telescope and its instruments. And there's also an extensive lower level documentation that you can find at jwstdocs.stsci.edu, which will tell you everything you ever wanted to know about the telescope or any of its instruments, how to make observations, how to analyze those observations or reduce them, what the formats of the data for the images or spectra are, and how to process them. And on the bottom, there's also the address for the data portal at the main STSCI archive, and very many of these web observations are publicly available, right off the bat, because a lot of the early observations came from special programs like ours, which was the early release science, and those observations all had no proprietary period, so they're all made public immediately after they were done. So as soon as these observations were taken, they were put on the archive, and anyone can get at them even as soon as we can, which makes for an interesting process for getting out papers and things like that, and pretty pictures that you like to show and hope that somebody else doesn't get to them first or something like that. But that's just the way it's been done with this telescope. But there are short proprietary periods involved with all of the observations that aren't immediately available, because the telescope is only going to last 10 to 20 years or something like that. And so the thing that you have to keep in mind is that discoveries happen in multiple steps. So we'll take an observation of Jupiter, and then somebody will see something interesting, and they'll have to make a slightly different observation, in a different wavelength or at a different scale or something like that, or a different time period. And after that, they will publish their findings, and somebody else will decide they need to do another observation to learn more. And you can only do this so many times with a telescope that has worst case or planned worst case of a 10-year lifespan. And hopefully it will be longer than that, because its propellant is actually lasting longer than they thought it would. And all of the coolers that work with the infrared detectors, which have to be kept very cold for them to work, are actually cooled with closed cycle coolers that use like Stirling cooling engines to move the heat away from the detectors. And the good thing about that is it uses power, but that's not a problem. But like many of the instruments on the Hubble, they required liquid cryogens like liquid nitrogen or liquid helium to keep them cold, and those only last so long. And so when those go away, you lose a certain amount of performance from your detectors, and you can only see certain wavelengths, or your noise level goes way up and you can't see very dim things. So because of that, if the propellant and the gyroscopes that actually point the telescope are probably the main limitations of its lifespan, and hopefully it will be a long and healthy one. So with that, I can take any questions anyone might have.
Yeah, Pat, and I've got the microphone, so if anybody has a question, raise your hand and I'll come to you with the mic. But Pat, I wondered if you could address a question that I have. Many of us in the nerd community followed the development and the years of delay, and then the launch, and then all of the deployment steps and single points of failure, or whatever they were called. And finally, the calibration images and then the first science. I'm wondering if you can speak, what was it like in your office? Were you guys popping champagne and chest bumping each other? What was it like being on the inside?
Well, it's usually just me in my office, so that would have been a pretty lonely activity. But there's a lot of things that went into this program which are slightly different from other programs. I'll just say that I first started my career at Space Science and Engineering Center working with Galileo. We had one of the probe instruments at University of Wisconsin, the net flux radiometer, which was on the probe which went to Jupiter. And you obviously know that there was the shuttle accident, which caused a great amount of delay in that particular program, and a lot of redesign of some of the instruments and some of their capabilities. And so I was sort of used to having things not go exactly the way they're supposed to time-wise. And the Webb was sort of like that too. Originally it was meant to cost only $4 billion or something like that, and be launched in the early teens or whenever it was. But those numbers all went up, the dollars and the years. And so when we first proposed for this set of investigations was back in 2017. And at that point, we were looking at an October 2018 launch. And so everything was happening very quickly. So, it was within like 4 months of when we put all these proposals together that they were selected. And with that, we had to, really start, digging into, how we're going to do the observations and working with people at Space Telescope Science Institute on the problems with the software, both the scheduling software and also things that they thought were going to go wrong with the instrument, things that they had found in ground tests on the lab, in the labs, and things like that, and workarounds we had to do. And so we're putting together all of these observations very quickly, and you have to know exactly what dates you're going to be able to view the planet, because if you're looking at the moons, you have to know where the moon is in relation to the planet or in relation to other moons and things like that. And for instance, if you're trying to look at Io in eclipse, in the moon eclipse, you have to know you only have 50 days of observing time, so you have maybe a dozen times when you can actually do your observation, and so that all had to happen quickly, and you're doing a lot of what ifs and things like that, so that you can make this observation happen at several different times with slightly different geometries and things like that. And then, as it turns out, the launch date slipped, and it went over budget, but it was probably for the best, because they fixed a lot of things with it. There were little hardware problems like screws and nuts and bolts and things like that, which they had issues with, and they fixed. And so eventually we got around to a December 2021 launch time, and as we were getting to that point, every time the launch would slip like 6 months, we would have to redesign our observations, because the deal was every 6 months you have to change your observations, just because you're either looking forward in the telescope's orbit or looking back, which means the telescope has flipped 180 degrees. So all of your mosaic steps go in a different direction, and the way the scheduling software is set up, you can't actually have just two different sets of all of these parameters. You just have to do everything all over again with slightly different angles, because the pole angle of Jupiter is slightly different, and that all has to happen. But and also, when you're doing something like tracking the Great Red Spot, you have to be tracking its longitude all the time, because that's not fixed. It sort of varies a little bit, goes faster or slower, and moves around a little bit. So that's something we had to update every 6 months or so as well. But as it turns out, when we finally got our Christmas of 21 launch date, we knew that we were probably going to get our observations in early July or in the end of June, actually, right around the time that Jupiter was 85 degrees away from the sun, and we could actually do it. And that was all a very exciting time, and we sort of, we have our fingers crossed that everything's going to work, but we also got lucky that some of the observations that they were doing for commissioning and calibration were also looking at Jupiter and as well. So we actually got a little foretaste of what things were going to look like, maybe not in the same filters or that sort of thing, but they used Jupiter, for instance, as a stray light target, so that they could see how close they could get to pointing to the planet, and still have the fine guidance sensors, which are the arrays on the outside of the focal plane, which are essentially tracking stars and are used to make the telescope follow the target that you're looking at. And they use Jupiter to do some of those stray light observations, and those actually became immediately available because of the way they had set up their data archive. So if you knew where to look, you could actually look at the first observations and see that, yes, it does work when you point it at Jupiter, and we were all very excited about that, and that kind of made a lot of it worthwhile, as did the observations when they finally came in and we got what, for the most part, we were expecting. And I'll just say that not all of the observations are even done yet. There's some that just happened a little while ago, and there's more that aren't going to happen until early next year. But as far as we can tell, all the instruments are working, and except for a couple of little exceptions, they're working to their specifications.
You're good.
Yeah, excuse me, about a two-parter here. It seems to me when shortly after JWST came online that there was a story or some doubt that one of the mirrors had been damaged. Is that true? And then the second one is, it's been up in space for a while now. Has there been any degradation due to micrometeorites?
Well, as you said, there was that little micrometeorite hit that happened early, and it did actually take a little chip out of one of the, hexagonal segments of the mirror, and it wasn't big. It was a little small portion, small hit, but it was noticeable. And one thing they do often is they take images of stars, and so that they can know exactly. You know that your star is a point source, so you take an image of it, and then you see what all the different diffraction patterns are, and how all of your mirrors are phased or unphased, and what should be a point, or actually a small diffraction pattern. You have these different rays and other artifacts going off away from the star, and they were able to compare images of stars from before and after and see that there wasn't a great amount of difference between the two, and they could actually, with new observations, they have new patterns of the stars that you can use to actually correct the blurring from all those different features. So when you look at a field of stars and you look at an observation of one particular star, you can use that one particular observation to what they call deconvolve the image and back everything out to point sources. Or if you're looking at a diffuse object, you can make the resolution much better and take out a lot of the scattering that occurs because of diffraction or because of dust and things like that on the mirrors, and scattering that occurs because of that. And as far as I know, the amount of scattering or anything like that off of the mirrors is not out of the ordinary or what wasn't expected. So they aren't having any long-term problems, and that one little micrometeoroid hit, hasn't caused any big problems at all.
Two-part question from Kevin online. First, what % of the micro shutters are stuck open and stuck closed?
I think it's less than 1%. So it's a pretty small number. Maybe a few hundred to a couple thousand, something like that. I don't remember off the top of my head. It's I think their goal was around 99%. And I think they got very close to that. And one good thing I'll say about it, if you look at the map of the shutter defects and things like that, down in the corner, like where some of the slits and the integral field unit are, those turned out to be actually very good portions of the arrays, which didn't have hardly anything stuck open. So where you would see like Jupiter impinging on the micro shutters, or where Jupiter was close to those micro shutter arrays, where you would see more leakage, and actually you end up getting a wide wavelength blurring over a wide wavelength. That was actually better than expected, and just because of the way it worked out with those micro shutter arrays. But they actually knew most of that, from ground tests in the lab before it went up.
Probably kind of answered the second part. When one wants the shutters open, are the ones stuck open still useful?
Certainly, if you happen to have an object there that you want to look at. I mean, if there's there are some places where there's little clumps of them open or something like that, and if you're looking at a cluster of stars or something like that, you can certainly put a star there if you want, and so I mean they can be used as regular open shutters if you want to. There's nothing else wrong with them. They're just an open door.
Anybody else?
Pat, it's been really great having you here. I know for myself and other members that we've been chatting, and there's been a lot of excited talk about James Webb for a long, long time. So we feel real fortunate to have you with us here this evening and share such very interesting information that we never get to hear about in the press. And I don't think to date there's been like a really extensive documentary on television to kind of look inside and see all these bits and pieces.
Yeah, I know there have been some. I don't know if they've done much with solar system observations with Webb, but I'd like to point out, this first address, webtelescope.org, which has lots of pretty pictures and things like that, and things go up there pretty fast, and they get some press release photos out quickly. And just recently, there have been observations of Neptune just within the last few weeks that occurred, and so there's, I think there's some real nice images up there of that, and that just happened recently. So there should be some nice stuff there.
Great.
And thank you for having me. And
it's our pleasure, and on behalf of the Astronomical Society, we'd like to offer you a small token of our gratitude that you'd be here tonight, and present you with the Madison Astronomical Society coffee mug.
Well, thank you very much.
Or anything else you'd like to put in it. Irish coffee or Long Island iced tea or whatever your poison is.
Right now, I think I'll just go for some water.
Yeah. Well,
all right. Thank you.
All right, so that concludes tonight's meeting of the Madison Astronomical Society, and we will see you here again on Friday, September 8th at the usual time. Have a good month, everyone.